We're almost done with Lewis dot structures. Last thing to talk about. And it's just the way the book does things, so we're going to stick with it. And if you take a look at these two structures, Lewis dot structures, right? And you could, are they resonance structures? Remember that kind of talk, Emily? Are these resonance structures? Well, you're right in the sense that you're moving a double bond around. We didn't move the atoms around, but the two oxygens that we move the double bond around aren't identical, right? So they're going to look different. I mean, right, the way they're drawn here, all the bond lengths are the same, and it looks exactly the same, but no. Real world, no, these really technically aren't resonance structures because those two oxygens aren't identical. Okay. So they're not getting at resonance here. So that double arrow is kind of misleading. What you're supposed to be doing is you're supposed to be picking one structure or the other. And everything looks like it's obeying the octet rule. So you do this on the exam, and I mark one of these wrong. And the only way you can figure this out is you pick the Lewis dot structure where all the formal charges are. You see the little red zeros written up there for every single atom. We need to calculate a charge, we're going to call it a formal charge, for each element in that molecule. And if you get all zeros, man, that's the best structure you can get. We're going to find out that if it's an ion, there's no way you can get all zeros. If the overall charge is +1, you add up all those formal charges, you're going to get a +1. So something isn't going to be 0, and that's just the best you can get. But the point is, the smaller the numbers, the better, and 0 is the best. So since this whole overall molecule has no charge at all, zeros for everything is the best answer. So the idea of these formal charges, see how here's a -1, the positive one, it's supposed to say, nah, not as good as this one. And the idea behind this is all these elements, do they have a similar tendency to attract electrons, Audrey? These are all covalent bonds. They're supposed to be sharing. Do they all play the same game? They all share equally, and they're all super nice. Or do some a little more selfish than others? I don't know how you want to put this, but right? Which element is the most electronegative, shares the least in these covalent bonds? Which element was it? F, fluorine. So that's the idea behind this formal charge. That's really the idea behind it. Okay. So let's see if we can figure this out. Using formal charges, select the best Lewis structure. So first, let's just do our general way of doing this, right? We add it up, figure out the total number of valence, make octets on everything surrounding. Anything left over, Lorena, we put these dots where? In the middle. On which atom would it be? On the phosphorus, on the P. So let's do that first. Let's add up all of the valence. Megan. Okay, add up all these valence for me. We've got 3 hydrogens. Each one has a 1. Okay. And then I've got 4 oxygens. 6. And I've got a P. 5. Okay, so 4 times 6 is 24. 3 is 28. Phosphorus has 5.
27.
It's 27.
Well, it's 32 is the total, but the oxygen and the
24.
is 27.
Guys, help me add this up. Mine's sicker than a dog here. 4 times 6 is 24. Yeah, I'm not going to, I was adding it up with an odd number, right? Because that's going to be 27, 32. My head kept saying 33. Got 33, I thought, shit, we're screwed. All right? Okay, 32. Thank you. All right, so connect everything, make octets and everything surrounding. See if there's anything left over, put it on the phosphorus. So did you end up, Kenneth, with anything left over to put on the phosphorus? Any lone pairs?
No, mine was
No.
I wasn't done.
Oh, you weren't quite done? But I just made octets on everything, and I'm hoping it works out. Did it? Okay. Okay. So no lone pairs on the phosphorus. So you're supposed to say, is that the best structure? Well, I don't know. Let's find out. The formal charge, calculate formal charges and find out. So how do you get these formal charges? What you do is you take the number of valence electrons on whatever atom. So you have to do this for every single atom. So we're just saying atom A. Pick phosphorus, pick an oxygen, whatever. So the formal charge on phosphorus is going to be the number of valence electrons for phosphorus minus the number of bonds that are going with phosphorus minus the number of lone electrons on phosphorus. So if I'm going to do phosphorus, right, it has, someone said that how many valence? Megan said it had 5, right? And then the number of bonds going to phosphorus has 4. The number of lone electrons? 0. So phosphorus should have a charge of what? Positive 1. Already it's not looking good because the word is neutral. Dylan, is this a neutral molecule? Does it have any charge? No, it doesn't have any charge. So you already know that, Kendall, the best answer is going to be all what for everything? All, anybody? All, helper? All zeros. So we're already kind of screwed. We know we're going to have work to do. Otherwise, I wouldn't have picked this one, right? Okay, so do that for every single element up there. Calculate its formal charge. Valence minus bonds minus number of lone electrons. And calculate a formal charge and put it next to every single element up there. So Connor, what would the formal charge be for that H? 0. Yeah, because you'd have, exactly. You'd have 1 minus 1 minus 0. So all those H's are zeros. Now recognize all these O's with an H on them, they're all identical, so you pretty much just have to do it once. So, oh, shoot. Rebecca, how did you get a formal charge for one of these oxygens with an H on it? How would you get it? Right? Number of valence. Valence on oxygen is 6 minus the number of bonds. What's the number of bonds with this? 2. So right now we have 6 minus 2 minus the number of lone electrons. The number of lone electrons is 4. So 6 minus 2 minus 4 is 0. So all those guys should be zeros. Now I've done this a bunch of times. I don't remember this answer, but I know that if I don't do this right, that oxygen sitting up there on top that we haven't figured out yet, it had better turn out to be what? It had better turn out to be minus 1, because they all have to add up to be the charge, or the overall charge on this thing. So if it doesn't come up to be minus 1, we screwed up somewhere. Okay? So number of valence would be, for that top oxygen, 6. Number of bonds is, everybody, 1. Number of lone electrons is 6. So it is. It's negative 1. Okay. So is it the best structure? Well, here's some hints. So all formal charges are as close to 0 as possible. So it seems like there's some improvement we could do. And the sum of all the formal charges equals the overall charge. I already kind of told you that. And the overall charge is 0. And that checks, though. That makes it okay. -1 and +1 is 0, but this one's a problem. A negative formal charge should be on. So if you can't get rid of all these, if you can't make them all zeros, make sure that the negative formal charge is on the most electronegative atom. Okay. Now that's kind of okay, because what's more electronegative, O or P? O. So that's okay, right? That one seems to check. These are good, but I think this is the problem. So we got to see if we can fix it. And the only thing that we have in our toolbox is to make a what? Make a double bond. It's the only thing we can do. It's not CNOS, though. CNOS is now thrown out the window. Formal charge rules the day. CNOS, though, I like CNOS. Why keep talking about CNOS? CNOS, I like CNOS because it helps you get to here faster, rather than doing all these different tests on everything. CNOS kind of gets you to the answer quick, just like the octet rule does. It doesn't always work, but it gets you to the answer the fastest. So make a double bond, and then see if it fixes the problem. So rewrite the structure and make a double bond to try to see if that changes things, and see if that fixes it. So we got to recopy this. We got an O, a P, an O, an O. Hold it. I forgot my structure. Yeah, that was right. And then we had H's. So there was our skeleton. See if that fixes it. Again, and your answer has to have, what do we say, 32 valence electrons on there, so don't mess with that. Remember, just erase the lone pair and erase it first, then make a double bond, right? So that's the only change we're making, because everything else was a nice 0. So let's recalculate this formal charge. Paul, let's recalculate the formal charge for the P. So the number of valence is 5 minus the number of bonds, which is 5. 1, 2, 3, 4, 5. Minus the number of lone pairs, which is going to be 0. There's no lone electrons. Not lone pairs, lone electrons. So that one checks. And then that oxygen, right? This oxygen. Number of, Giselle, valence? 6 minus bonds. 2 minus lone electrons. Yeah, there's 4 dots on there. 2, 3, 4. So it'd be 4. And then you get 0. So everything's 0. It works. So this is the best structure, right? That's the best structure for phosphoric acid. Okay. Use formal charges. Don't disregard CNOS and the octet rule, though, because that'll get you here the fastest to the right structure. But as a last final check, you got to do formal charges. Okay, so before we go to the boards and start messing with this stuff, the book threw this in. I don't know, maybe because there's no other place to put it. I don't know. You can get the enthalpy of a reaction. And remember, we called them thermochemical equations, right? We had these reactants. And then they go to products. And then we had a delta H for that reaction. So, and we had like 2 or 3 ways to get the enthalpy for a reaction. So here's another way. What you do is have a nice table like this. You can't do it without this table. And what you do is you find all the bonds that you're going to break for this reaction to proceed. Identify all the bonds you're going to break and find them in this table. Add them all up. That's what the sum is. The sum of the bond energies broken. Okay. And then you identify all the bonds that you're going to form. Find them in this table. Add up all of theirs. Right? and then subtract those two sums, and you'll have an answer. Now, when you get these numbers in the table, Mia, can you read it? What are the units? For all these, there's a lot of numbers in that table, but what are the units of those numbers? Can you read it? Kilojoules per mole. Good, because that's what delta H is in, right? We'd have a real problem if it wasn't. So, okay, so let's see if we can do this. Now, I'm going to go against my own advice here. And my advice is usually, because I end up screwing this up every time, usually I just say break everything and form everything, because then you can't screw up, right? But that's not how you guys like to do it. You like to do, you feel like it's the least work if you don't do all that. It sounds like it's extra work. I say it's not, because I never screw up. But anyway, let's try it, the way I know you guys are going to do it. You're going to identify just the bonds that were broken. Okay, so if I want to break bonds, am I supposed to be looking at the reactant side or the product side? The reactant, right? Because the reactant has to break. Okay, so what bonds, let me circle them, Manuel. So here's my reactants. Which bonds should I be circling? Because I want to break them. That C double bond C. I definitely got to break this. What else do I got to break? Anything else? Or am I done? That H2. Yeah, there's really an HH there. Okay. Do you see any other bonds, Sydney, that I got to break? Sydney? No? Okay, so bond energy is broken. Find them in the table and put them in here. Okay? Find them in that table and then put those numbers in there. Let's see if you're reading that table right. Alyssa, what did you put in for the double bond? 602. You're reading the table right. Good deal. And then we have we had to break Bowdy that H2 bond. What number did you put in? 432. Very good. So if you're not seeing where these numbers are coming from, ask. Okay. Now, Kendall, we're supposed to subtract, so I wrote the subtract sign in there. The bond energy's formed. Okay. So let's circle the bonds that we're going to form. What would you circle? Exactly, I would too, because nothing else changed. Okay. So, Lauren, what would you put in the sum then? Yeah, it has to be CH bonds. All right, do you see it? Would have to be 411. And just once? Twice. Right? Okay. And then that's it. That's your answer. Okay. 602 plus 432 minus 411 times 2. I guess we should finish this. (602) plus 432 minus 411 times 2. I got 212. And if you don't put on units, you're going to lose points. So it's an endothermic reaction. Okay. Audrey, make sense? Okay. So I'm sure there's going to be some homework on that, but the majority of it is this stuff. So see if you can help each other out at the boards and ask if you're not sure. See if we can come into a consensus for the answers for all this stuff.
Can I check the lab really quickly?
Hmm?
Can I check the lab quickly?
Oh, yeah, yeah.
Thank you.
So let's start with A. Do A first. Write the best Lewis structure. Let's see. Let's write up here somewhere so you forgot what the formal charge equation was. Formal charge, number of valence minus number of bonds minus number of lone electrons. Okay. I would write a Lewis structure first and follow that general idea, right? Where you make octets and everything surrounding, anything left over, put on the center atom. That's your starting point. And you see if that's your right answer. Okay? See if that's your right answer. Because otherwise you could be at this all day. So start with figuring out the number of valence and okay, if that's your as long as he has the right number of valence, now just do formal charge and everything. Does it have the right? How many valence are you supposed to have?
26.
26. Does it have 26?
7.
No. Still needs.
So make sure you have the right number of valence. And then calculate formal charge for everything and show your formal charge on everything. So your final answer should have 26 valence electrons, right? And then calculate a formal charge for everything. Since this is a neutral compound, the best answer is going to have all zeros for everything. 2, 4, 6, 8, 10. Yeah, that's 26. And you got 0 for everything. That works. Good deal. I think you have too many dots. Like before you erase, see how 2, 4, 6, 8. 2. Oh, that's your 0. All right.
I did the same thing when I looked at it because it was 0.
All right. Good. Good, good, good. I see a... Is that it? And there's a lone pair on that. So I'm just copying Bowdy's answer there. All right. And then you calculate formal charge on everything. 0. Okay. And then now recognize in B, when you get to B, bromate, it's an anion. It's going to be impossible to get zeros for everything. And you don't want to get zeros for everything in the first place, because you add them all up, you better get a -1.
still 6.
Oh, that's 26 though.
I was able to do double bonds.
Okay, if you have 26 on here?
Yeah, I just didn't put the 7 on
Well, get 26 on there first. All right. Well, now you have 20. Now you. Whoa. Because you have 8 and 8 is 16 and 8 is 24 and 2 is 26. So there's your 26. Now, what I think you should do is get a formal charge for everything and see where you can improve things. So how many valence electrons do you have? 26. Oh, that's a 0. Keep looking at these as dots. Yeah. 8, 2, 4, 6, 7, 8, 9, 16, 24. Well, you have like 28 electrons on there. Yeah, so each oxygen is -1, you're saying?
Yeah.
So -1, -1, -1, that's -3, and a +2 is -1. So you're doing this right. So they all add up to be the charge. So the thing is you just want to get everything as close to 0 as possible. So if you can make these, the best answer would be zeros for everything and a -1 on an oxygen, because it's the most electronegative. That would be the best possibility. So see if you can get that. So I'm gonna copy Paul's here. You had a lone pair on there, right? On the bromine, Paul? There's a lone pair on the bromine? Oh, 2 of them. It's 3, 2. Oh yeah, 2 dots. Okay. So when you start out, 24, that's 26. When you start out for this bromate, I think he got -1s for formal charges for all these oxygens and a +2 for the bromine. So this works because you add up everything, you get a -1. Except, remember the rules, you want to get as close to 0 as possible. So for something like bromate, the best possibility is going to be zeros for everything and only one element with a -1. And make sure that -1 is on the most electronegative. So that's kind of your goal for this. See if you can get zeros for everything except for one, essentially oxygen, because it's more electronegative than bromine on the periodic table. So you should have zeros for everything except for one of those oxygens. Have it be a -1. That's your best combination, if you can get that.
If it comes out like that, then do it 3 times. It was showing it like that.
Oh, that would be resonance. But
do that together, no?
if it asks for resonance structure, show all resonance structures. But clearly show all your formal charges. So that works. So you got zeros for everything but that one. Okay, yeah, it looks good then. All right, good deal. Yep. Okay. Yeah. I think that's as good as you can get it. Good. I think that's it. And then you got to have brackets with a -1. Yep. I think that's good. So I think some folks are figuring this out. It doesn't matter where, but have 2 double bonds for that bromate, right? Is there anything on the bromine? Did you have anything on the bromine? Is there a lone pair on the bromine? There is? Okay. 2, 4, 6, 8, 16. Okay. So I think that's the best answer because then you have, all right, this guy's a -1. These guys are zeros. So that would be your best answer. Well, you follow CNOS because hopefully it gets you to this the fastest. So it's still a little bit of a guide, but it's not the final check. Formal charge is the final check. Yes, you have to because the whole thing. Remember, it's bromate, BO3 minus. Yeah, so you should draw brackets around this whole thing and write a -1 because it has a -1 charge.
We put way more than we needed on that chlorine.
CLO.
For this, I didn't understand why O just had 2 bonds.
Oh, because you just, this one?
Mm-hmm.
1, 2. So you just look at the lines that are drawn to that element. Like this P has 1, 2, 3, 4 bonds to it. This H only has 1 bond to it.
Oh.
Just count the number of lines drawn to it.
So even like this, since this just has 1, we just look at the one with the most?
Because each oxygen has its own formal charge. So this oxygen has 1 bond to it.
Mm-hmm.
This oxygen has 2 bonds drawn to it. So does this one, and so does that one.
Oh, okay.
Does that make sense?
Yes, thank you.
So did you get an answer for NCLO? A triple bond?
We have 2 different answers.
There might be more than one. So let me copy this one down. Did this one work? A triple bond? Let's write down this. See if we can find something wrong with it. 2, 4, 6, 8, 10, 12, 14, 16, 18. That has 18. Nitrogen has 5 minus 3 minus 2. Chlorine is 6 minus. Well, they all have zeros. That works. Is there another possibility for NCLO?
Oh yeah, I have a single bond between NCl and then a double bond between Cl and O.
Okay.
And then I have 4 on nitrogen, and then 4 on Cl, and then
4 bonds on the chlorine. 4 lone electrons.
yeah, and then 4 on oxygen.
Let's see. So we have to use up 18. 2, 4, 6, 8, 10, 12, 14, 16. Yeah, that works. Yeah, use up 18. And everything is 0 on that one too?
Yeah.
Wow. Is there any other answers you guys got? For NCLO? Okay. Try HOCLO, HOCLO. Saw you guys practicing. Were you out there hitting in the batting cage?
Oh, yeah. Yeah. You jog by there?
Jog.
Oh, okay.
For HOCLO. Dylan, what'd you do for HOCLO?
Just added a double bond to that over there.
Then you got 20 valence. 2, 4, 6, 8. Yeah. Huh.
I don't know, you said it so fast, I didn't even get to look at it before it went. Wait, oh, there's another,
So you Dylan, you had a double bond between chlorine and oxygen?
Yes.
And what were the lone pairs on chlorine?
There's 2.
2 of them. And oxygen had 2 also.
Yeah.
6, 7. Yeah, that works. There's only one left. Anybody get E? What'd you guys do for E? Chlorine and oxygen? They both had double bonds? And then you had 2 lone pairs on each one?
Yeah. And then 1 lone pair on chlorine and then chlorine.
3 lone pairs, right?
Yeah.
Does everybody agree for E? Good deal. All right, have a good day.
Sir, if you find a lab manual, it's fine. Your face was in the way.
Okay.